Alright, we attempt to finish up section 6 of chapter 10 with one more video. We did an example using parametric equations with linear motion in the previous video, so we're going to look at one with projectile motion. So I had already written this out in the previous video for you to see, but I went ahead and just wrote it out again. That way you can refer to this, because we're going to use this as we're going to do the story problem over here that involves projectile motion, a cannonball being launched from a cannon. Alright, now notice x sub 0, y sub 0, initial position. We mentioned that before. Here are our two variables. X is equal to v sub 0 cosine theta, t plus x sub 0. This is the initial speed. This is the launch angle. And this is the initial x position as far as the horizontal. And then y is equal to negative 1/2 gt squared plus v sub 0 times the sine of theta, t plus y sub 0. G is gravity. And so that's going to be either 32 feet per second or 9.8 meters per second. Again, it should be negative, but they've accounted for the negative here in the negative 1/2. V sub 0, again, the initial speed. And theta again, the launch angle. And of course, y sub 0 is the vertical position, initial position. So we have a cannonball is launched from a cannon at an initial height of 1 meter at an angle of 30 degrees to the horizontal with an initial speed of 200 meters per second. We're going to write parametric equations to model the path of the cannonball as a function of time. Well, we've got all sorts of information here. We say we have an initial height of 1 meter at an angle of 30 degrees. So what I did, and you can see maybe over here, although it's not a very good looking cannon, is that I set this up so that the cannon fires the cannonball 1 meter above, so 0, 1, I'm putting it right here 1 meter above the origin, and the 1 is representing 1 meter. And as you can see, it's got a bit of a parabolic path there, and it lands somewhere way far here, which is one of the questions that they actually ask. And we have a 30-degree launch angle, so if I was to, this would be 30 degrees. So our 30-degree launch angle, that means theta is 30 degrees. We have an initial height, so x sub 0, y sub 0. We have an initial height of 1 meter here, so we're going to use 1, 0. So x sub 0, y sub 0 is, I just said 1, 0, I meant to say 0, 1. And what else do we have? We have the initial speed, that's v sub 0. That's 200, and notice it's in meters per second, so gravity is going to be 9.8 meters per second. And I think that is all the stuff we need. So here, oh no, yes it is. So let's find our parametric equations here. We'll start with x. X is equal to v sub 0, which is 200, times the cosine of our launch angle, 30 degrees. I happen to know what that is. All that times t plus x sub 0, which is 0. So this is going to give me x is equal to, well that of course is 0. The cosine of 30 degrees is the square root of 3 over 2 times 100, or 200 would be 100, the square root of 3 times t. Oh, I said 100 and I wrote down 1,000. That's not going to work. There we go. So I have 100 square root of 3 times t there. Now the little bit more complex one is y. Y is equal to negative 1/2, and that's times 9.8 for gravity, t squared, plus v sub 0, that's still 200, and times the sine of 30 degrees, our launch angle, t, plus y sub 0, which is 1. So this becomes y equals negative 4.9 t squared, that's this part right here. Now the sine of 30 degrees is 1/2, so 200 times 1/2 would be 100 plus 1. And so this guy right here and this guy right here are the parametric equations that's being asked to model this path of the cannonball as a function of time. Now we have some interesting questions. Once we have these parametric equations, there are other questions about this that we can answer. It says, for example, in part B, for how many seconds is the cannonball in the air? Well, the cannonball is in the air until y, the height, is 0. So I'm going to take negative 4.9 t squared plus 100 t plus 1, and I'm going to set it equal to 0. And this is not going to factor. I'm going to have to use the quadratic formula. T is equal to the opposite of b plus or minus the square root of b squared minus 4 times a, which is negative 4.9, times c, which is 1, all over 2 times over 2a times negative 4.9. So now, I would definitely need a calculator to do this, but I kind of worked this one in advance, and I got this to be t is equal to approximately negative 0.1 or negative 0.01, which doesn't seem like a likely answer because that's a negative time, unless of course you're in the twilight zone. Now there are two answers, one with plus, one with minus, and the other answer turns out to be the answer that we're looking for, and it's 20.42. Remember, this is in seconds. So for how many seconds is the cannonball in the air? Well, it hits the ground 20.42 seconds after it's been fired. So the cannonball, I guess it's actually two words there, is in the air. Oh, I'm writing very sloppy. Sorry about that. Is in the air for 20.42 seconds. Don't forget your units. All right, and it's a story problem. Answer your question in a short sentence there. Now, part C, it says determine the horizontal distance traveled by the cannonball. Well, the horizontal distance is determined by the x values, and so we know that it's in the air for 20.42 seconds until it hits the ground. So we would need to know the x value here at 20.42 seconds. So x at t equals 20.42 seconds is equal to 100 times the square root of 3 times 20.42. Of course, this would be an approximate because this was an approximate. And again, you would want to have a calculator close by. That's really kind of messy there. And I did this in advance, and I got this to be, I wrote it down here so I could write it here, 3,536.95, or no, 85, excuse me. So that means that this cannonball went to the total distance. Now it went up in the air and it came down, but the total horizontal distance, it landed over 3,500 meters away. So determine the horizontal distance traveled. The cannonball traveled horizontally a distance of 3,536.85, and remember this is in meters, so write out your answer, short sentence there. And so far so good. So we used this parametric equation once, we used this parametric equation once. I wonder what the next one's going to yield here. When does the cannonball reach its maximum height? Well, height would be the y, and because the y is a parabola here, you can see it's a quadratic function. It's going to reach its maximum height at the vertex. Now notice here A is negative, it's going to open downward, so the vertex is kind of the highest value. So I need to find, because it says when, I need to find the value of t, and that's where we can use t is equal to the opposite of b over 2a. Well, in this case A is negative 4.9 and b is 100. So this would be negative 100 all over 2 times negative 4.9, or negative 100 all over negative 9.8. So that's almost 10. Negative divided by negative is positive. It should be just a little bit more than 10. and this would be in seconds. So again, you need your calculator here. We'll take it out, and I got this to be 10.20 to the nearest 100 seconds. So the cannonball reaches its max height 10.20 seconds after it is fired, or after the cannon is fired. Okay. Then it says determine the maximum height. Well, the maximum height goes back to here. What value do we plug in? Well, we get the maximum height at 10.20 seconds. So we would need to figure out what y is when t is 10.20. So this is going to be negative 4.9 times 10.20 quantity squared plus 100 times 10.20 plus 1. And again, need a calculator. I got this to be 511.20. 511.20 the first time I did this. So that's going to be, that's up there, 500 meters? Man, this is a powerful cannon. So the cannonball reaches a maximum height of, don't forget your units, 511.20 meters. And even though it was just one problem, we were able to break it down into different parts and ask different questions. And you can see how convenient it was to answer parts B, C, D, and E using the answers here in part A, the parametric equations. So definitely very useful when solving certain types of motion problems. So that kind of finishes up this section. Remember, practice, practice, practice.